Hi, welcome to lecture 6. This lecture will be about prime ideals and the lying about theorem. This lecture will be about prime ideals and the lying about theorem. So the setting is the following, and I'll assume this setting throughout this lecture. And I'll flip the direction. So on the left hand side, I'll first have the inclusion of fields, L over K. Inside K, I have this domain A. And I have B, which is integral over A. So the setting is that B is integral over A. And suppose furthermore I have a prime ideal in A, and the question is, can I lift it to a prime ideal in B? So the weight question is, can you lift a prime ideal in A to a prime ideal of B, and what does that mean? So observe that if you have a prime ideal Q of B, you can intersect it with A, so it turns out to be a prime ideal of A. And why is that? Well, if you take two elements x and y in A with the property that the product belongs to Q intersect A, but the intersection of Q and A sits inside Q, which sits inside B, and since Q is prime, this implies that, well, we have the product x times y is in Q, so either x is in Q or y is in Q. Okay, but x and y are in A as well, so either x is in Q intersect A or y is in Q intersect A. Okay, so if you start with a prime ideal of B and intersect it to A, then you get a prime ideal of A, and we say that a prime ideal Q lies above P if its intersection with A gives you P. Okay, this is the definition. Okay, and so the question is, so given a prime ideal P, can we always find a prime ideal Q in B that satisfies this condition? So the question is, does the lying above property hold for integral extensions? What does that mean? So assume the above setting throughout. So given a prime ideal P of A, does there exist a prime ideal Q of B with the property that Q intersect A equals P? In other words, it lies above P. Okay, so what are we searching for? So we are searching for a prime ideal Q of B. Now, when you intersect it with A, it equals P, so it does not intersect A minus P at all. So in other words, its intersection with A minus P is the empty set. but Q contains Q intersect A, which equals P. So in other words, Q contains P. It's an ideal in B, so it contains P times B. And what is P times B? So by definition is P times B is the smallest ideal of B containing P. And every element of P times B is of the form summation Pi Bi, as I goes from 1 to say some m, for these Pi's in the ideal P and these Bi's in B. Okay, and just caution, even though P is a prime ideal in A, the ideal, when you extend it to B, the ideal P times B need not be a prime ideal in B. Okay, and I want to recall one fact about prime ideals. So if P is a prime ideal of A, then in this first property I was looking at A minus P. So what's the significance of the set A minus P if P is a prime ideal? So the set A minus P is multiplicatively closed. So if you take two elements of A minus P and you multiply them, you get another element of A minus P. So why? Suppose you have two elements which belong to A minus P. That just means that S1 doesn't belong to P and S2 doesn't belong to P. Okay. Now I want to show that it's multiplicatively close. So if the product does not belong to A minus P, then the product must belong to P, but P is a prime ideal, so this implies that S1 belongs to P or S2 belongs to P, and this contradicts the assumption that both S1 doesn't belong to P and S2 doesn't belong to P. Okay, so this was just a short recap that if P is a prime ideal, then A minus P is a multiplicatively closed set. Okay, so I want to prove this lying about theorem. So we'll warm up with a lemma. So I have this ideal P times B. I have this multiplicatively closed set A minus P. So the first thing I want to show is that its intersection is the NP set. Okay, why? So suppose not, for the sake of contradiction, so suppose you have an element little s in A minus P which also belongs to P times P. Okay, and since it belongs to P times P, you can write little s as the summation Pi Bi for this finite sum from 1 to m for some Pi's in this prime ideal P of A and this Bi's in B. Okay, and you write C as the subring of B generated by B1 up to Bm. because this is the smallest subring of B containing A and B1 up to Bm. And it's a ring, but it's also a module over A, and we had this trick from previous lectures to show that it's finitely generated. So I'm just going to quickly recall the trick to show that C is a finitely generated A module. So A sits inside A adjoint B1, which sits inside A adjoint B1, B2, and so on and so forth. It sits inside A adjoint B1 up to Bi, which sits inside A adjoint B1 up to Bi plus 1. And you can go all the way up to C, which is A adjoint B1 up to Bm. Okay, and if you call the ith term Ai and the I plus first term Ai plus 1, so the first term is A1, the second term is A2, and so on. So this trick was just that each Ai plus 1 can be written as Ai adjoint Bi plus 1, and Ai plus 1 is a finitely generated Ai module, since Bi belongs to B, and since Bi belongs to B, it's integral over A. But if you're integral over A sits inside Ai, so you're also integral over Ai. And so by just using this transitive property, we could conclude that C is now a finitely generated A module. So you have a finite generating set as a module for C. It need not be these Bi's, it could be something else, but you have a finite generating set. So let's call it W1 up to Wt is a finite generating set for C as an A module. Okay, and just an observation that since C contains A, it is non-zero, and in particular one of the Wi's must be, at least one of the Wi's must be non-zero. Okay. And observe that if you have an element in C, then you can multiply it with S, this little s, which had this formula that it was, this little s was pi bi, summation as I goes from 1 to m. But then observe that if you put the brackets around bi times c, little c is in C, the bi's are in C, and the pi's are in P. So this product is in C, and pi's, they belong to P. So notice that little s times little c sits inside P times C. Okay, that is little s times this ring C sits inside P times C. Okay, now expanding this out in terms of the generating set. So we have W1 up to Wt is a generating set for C. So in particular S W1, you could write this as, in terms of its generating set, let's say x11 W1 plus x12 W2 plus so on and so forth x1t Wt. SW2 is x21 W1, x22 W2, and so on and so forth. And similarly, SWT is xt1 w1 xt2 w2 and so on and so forth xtt wt, where these quotients xij's. So observe that little s times c is not only in c, it's in p times c. So all these coefficients are in fact in p, which sits inside A. Okay, and again using a trick as before, writing this in matrix form. So if you write this in matrix form, you have little s times this column vector w1, w2 all the way up to wt equals the matrix x11, x12, so on and so forth, x1t, x21, x22, so on and so forth, x2t, so on and so forth, xt1, xt2, so on and so forth, xtt, times this column vector w1, w2, so on and so forth, wt. And so let's call this T cross T matrix X. So this matrix X is a T cross T matrix in A, but in fact all the coefficients are in P. Okay, and this column vector W1 up to Wt is a non-zero vector because at least one of the coordinates is non-zero. So what do we have? So W1 up to Wt is a non-zero eigenvector for X. With eigenvalue S. Okay, so S must satisfy the characteristic polynomial of X. And which is a monic polynomial but notice that all the coefficients of this matrix are in this ideal P. So all the coefficients of this monic polynomial should lie in P as well, since P is an ideal. Okay, and so if you just expand this out, expand this characteristic polynomial out and substitute S, what do we get? S to the T plus A T minus 1 S to the T minus 1, so on and so forth, A1S plus A naught equals 0, where all these coefficients AI are in this prime ideal P. And if you just rearrange, what do we get? We get S to the T equals a negative sign, AT minus 1 S to the T minus 1, so on and so forth, A1S plus A naught. Okay, but if you look at the right hand side, each of these coefficients are in P, so this linear combination of these coefficients should also belong to P. Okay, so what does that mean? That S to the T should also belong to P, but P is a prime ideal, that means S belongs to P. Since P is prime, you can write S to the T as S times S times S T times. Okay, but this is a contradiction. that S in fact belongs to A minus P, and hence S doesn't belong to P. Okay, so we've arrived at a contradiction. So this proves the lemma that PB intersect A minus P is in fact the empty set. Okay. So now you look at sigma, which denotes the collection of all ideals of B satisfying the following properties. So the first property is that the ideal I contains PB, and its intersection with A minus P is the empty set. And what lemma 11 tells us is that this collection sigma is non-empty. As we've shown that P times B, this ideal P times B, is in fact in sigma. Okay. So the next result I don't want to prove. I'll leave it as an exercise. It's an application of Zorn's lemma, which is also something that you encounter in abstract algebra. So show that this set sigma has a maximal element under the partial ordering given by inclusion. Again, the hint is to use Zorn's lemma. Okay. So I'll leave this result as an exercise. And the next lemma is to use this exercise. So suppose you have a ideal which is a maximal element under inclusion. So when I say maximal, it means it's under the inclusion property of sigma. Then the claim is that this element is a prime ideal of B. Okay. So let's prove this lemma. So suppose not, for the sake of contradiction, so if J is not a prime ideal, that means there are two elements, X and Y, in B with the property that X is not in J, Y is not in J, but the product X times Y is in J. Okay, so we want to use the fact that J is a maximal element of sigma. So you construct new ideals, which I'll call J plus X, which is, by definition, it's the smallest ideal of B containing J and X. Okay, and since we have that X is not in J, this ideal IX strictly contains J. And every element of this ideal is of the form alpha plus beta X. This alpha is in J and beta is in B. Okay, and similarly you let IY denote j plus y. And again, this is the smallest ideal of B containing j and y. And just as earlier, since y is not in j, what do we have? We have that Iy strictly contains j. Okay, and so since Ix and Iy strictly contain j, they cannot belong, both of these ideals cannot belong to sigma. Okay, so recall that the ideals in sigma have two properties. What are the two properties? It should contain PB, and its intersection with A minus P should be the empty set. So now Ix, well, it contains j, and j belongs to sigma, so it satisfies its first property that it contains PB. Okay, since j belongs to sigma, the first property tells us that j contains PB. Okay, so Ix also satisfies the first property for the elements that sigma satisfies, but since Ix does not belong to sigma, what's left is that it cannot satisfy the second property. So Ix does not satisfy property 2, that is Ix intersect A minus P is not the empty set. So in other words, there exists an S1 in A minus P such that S1 also belongs to Ix. Okay. Now similarly, you can play the same game with Iy. Iy by definition contains j, which contains PB, and since Iy is not in sigma, so Iy intersect A minus P is not empty. Okay, so thus there exists S2 in A minus P with the property that S2 also belongs to Iy. Okay, now let's unwind the definitions of what it means for S1 to belong to Ix and S2 to belong to Iy. So we can write S1 as alpha 1 plus beta 1 x and S2 as alpha 2 plus beta 2 y, where alpha 1 and alpha 2 belong to J, beta 1 and beta 2 belong to B. Okay, and since P is prime, we have that the set A minus P is multiplicatively closed. So thus S1 times S2 should belong to A minus P as well. Okay, but we can use the definitions of S1 and S2. S1 is alpha 1 plus beta 1 x, and S2 is alpha 2 plus beta 2 y. Now if you expand this out, you get alpha 1 alpha 2 plus alpha 1 beta 2 y plus alpha 2 beta 1 x plus beta 1 beta 2 times xy. Now both alpha 1 and alpha 2 are in J, so the product belongs to J. Alpha 1 is in J, so alpha 1 times beta 2y, that belongs to J. Again, alpha 2 is in J, so the product alpha 2 times beta 1 x is also in J. And now by assumption, x did not belong to J, y did not belong to J, but the product belongs to J. So this last term also belongs to J. So each of the 4 terms belongs to J. So what we have is that S1, S2 belongs to J, but it also belongs to A minus P. But this is a contradiction because since J is in sigma, you look at property 2. What does that give us? What does that property give us? It tells us that J intersect A minus P is the empty set. But we've just produced an element S1 times S2 in this intersection. So this provides a contradiction. And this proves a lemma. That this maximal element is a prime ideal. And so the final theorem is that the lying above property holds for integral extensions that is, what we've shown is that this prime ideal J so J is a prime ideal of B that lies above P. Okay, and the proof is very quick. So by the previous lemma, J in fact is a prime ideal. And what do we have? J contains PB since it belongs to sigma, and PB contains P. Okay, so this means that J intersect A should contain P intersect A, which is in fact just P. Okay, so J intersect A on the one hand contains P, but what we also have is that J intersect A minus P is the empty set. So the intersection of J with A must be completely inside P. Okay, so thus we have that J intersect A is in fact equal to P. Okay, and this proves the theorem. Thank you.